Let's continue section 22.5. So in this section, we're looking at ways to alkylate or put carbon chains on the alpha position of a carbonyl compound. And I told you there were 3 different alkylation reactions. The first one we looked at, alkylation via enolate, which is just an SN2 reaction. The second one that we're going to look at is called the Malonic ester synthesis. This reaction uses a really specific reagent. This is kind of unusual because a lot of times we have options about the starting materials for our syntheses. In this particular reaction, we always start with this compound, which is called diethyl malonate. It's a diester, as you can see. It's got ethyl groups on it. Its common name is Malonic ester. And so this reaction is either a 3 or 5 step reaction, one or the other. I'm going to draw the 3-step version first. And in this reaction, step 1 is always an ethoxide. Sometimes it's written as sodium ethoxide. Sometimes it's just written as OET minus. And the step 3 is always H3O plus heat. So these reagents that I have written here in blue, these are always going to be exactly the same every single time you do the malonic ester synthesis reaction. The only thing that you have the option to change is this: in step 2, we're going to add an alkyl halide. And it can be the alkyl halide of your choice. Pretty much, it is still an SN2 reaction, so you've got to make sure it's not too bulky. So this reaction produces a carboxylic acid. Seems like it's magic, but we're going to look at the mechanism, and the mechanism is really clear. And it adds that R group from the alkyl halide to the alpha carbon. So what I want to do, so one of the questions you have on sapling is asking in the product, when you're looking at the carboxylic acid product, which carbon atoms actually came from the diethyl malonate. So these 2 carbons right here, and also this carbonyl group. The sapling question is not asking about that. And this, this bond here too. So this is what is retained when we're doing this malonic ester reaction. The rest of the molecule is lost. And so you get to choose. This is a way of making a carboxylic acid that's got a long carbon chain on it. That's the 3-step version. The 5-step version you would use if you wanted to add 2 alkyl groups to the alpha position. And so for the 5-step version, you basically repeat step 1 and 2. So you do sodium ethoxide and then an alkyl halide of your choice. And then you repeat sodium ethoxide again. And let's use a different color. Let's do another alkyl halide of your choice. Maybe they're the same, maybe they're different. And then you finish it up with H3O plus and heat. You still make a carboxylic acid. And of that carboxylic acid, the same 2 carbons are still coming from the diethyl malonate. So that part is still the same. But with this reaction, you have added 2 R groups to the alpha carbon. And so I want to make sure it's really clear. How can I make this really clear? That this carbon and this carbon, this carbon and this carbon, they both came from the original ester. Maybe that makes it easier to see. Ooh, too much. So let's look at the mechanism for this reaction. We're going to do, we'll do the 5 steps just so you can see the whole thing drawn out all big. And remember again that we always start with diethyl There's no other option here for this starting material. And we also always start with ethoxide. It's the only base that we want to use, and this is consistent with stuff we were doing yesterday, like matching the R group of the OET, matching the OR groups of the ester and the base. So this first step is going to deprotonate at the alpha position, just like you would expect. And this is a doubly alpha position because there's carbonyl groups on the left and the right, so it's very willing to get deprotonated. And we make this enolate, and then we bring in an alkyl halide. Let's just do, for the first one, let's do CH3Br, and this is just going to do an SN2 and add that first R group to the malonic ester, like that. And we still have that alpha hydrogen there. Go ahead and draw that guy back in. So if we were doing a 3-step reaction, we would be done with this aspect of it, but since we're going to draw the mechanism as if it was 5-step, then we bring the ethoxide back again, and we take off that second alpha hydrogen, and we make another enolate. Like that. And now we're going to bring in a second alkyl halide. So let's do something different this time. Let's do like this guy right here, an isopropyl bromide. And another SN2 reaction to add that second alkyl group. Like this. And there are the 2 alkyl groups right there. So once we get both of the alkyl groups in place, then we bring in our H3O+. Now this, what happens here, this is a reaction that you already learned in chapter 21. This is the hydrolysis of an ester. So this reaction is just going to convert the ester, both of the ester functional groups, to carboxylic acids, a mechanism that you have seen, and maybe you want to go back and look at it again if you've forgotten it, which is fine. But that's what's going on in that step. Now, what happens next is something that's super magical and awesome. And in order for us to visualize the next thing that happens, what I'm going to do is redraw this dicarboxylic acid. So all I'm doing is redrawing it, and I'm redrawing it because it's going to make it easier for us to visualize. So the left side of the molecule, you can see I didn't make any changes to that, and I don't make any changes to the alkyl group. But what I'm going to do is twist the right carboxylic acid group. I'm just kind of turning it around. I'm reorienting it, not changing it, just redrawing it to make it easier for you to see what's going to happen next. So what we find is that when we have a molecule that has this type of shape where it's a dicarboxylic acid and it has a carbonyl group and a second carbonyl group that are separated by just one alpha carbon, and it can twist itself up into this shape that, as you can see the way I drew it, it resembles a 6-membered ring. It can perform this, basically it's going to look a lot like a Diels-Alder type of a reaction, this reconfiguration of electrons. I'm just going to, pretending like it's a Diels-Alder, start with one of the double bonds, or the only double bond. I'm going to start with a bond, and I'm going to move it clockwise or counterclockwise. It's not going to matter how you move it. Switch to the next bond and move it. Switch to the next bond and move it. So it really looks familiar. A lot like kind of like maybe the Cope rearrangement or something like that. And let's redraw what we get when we get that shuffling of our bonds happening. So our carbon-oxygen double bond turned into a single bond, and the bond next to it became a carbon-carbon double bond. Nothing happened to those two alkyl groups. The next carbon-carbon single bond was broken. Carbon-oxygen single bond became a double bond, and then we still have that other carbon-oxygen double bond hanging off of it, and that looks really weird, but it's not as weird as it looks. We broke the the hydrogen-oxygen single bond, and we created a new oxygen-hydrogen single bond. So this is rearranged. There's two parts, rearranged. I'm going to redraw this to make it look cleaner, because we've got some weird bond angles going on there. So that alkene slash diol, which has more normal bond angles associated with it, and this guy, which looks really weird, is carbon dioxide, a CO2. It just looks really funny in line structure. So this is an alkene slash alcohol, which will do a tautomerization, a hydride shift. This is a keto enol tautomerization. The last time we looked, I think the last time we looked at the keto enol tautomerization was way back in the fall quarter, at the end of the fall quarter, when we were looking at reactions to alkenes, addition reactions to alkenes, and we would have an alkene, and then we would add water to it, and we'd end up with this enol, and then we would see that the enol would tautomerize itself, switching the carbon double bond to a carbon oxygen double bond, because that's more stable. So the reaction looks really magical, and I think it's a really awesome mechanism. It's not necessary that you draw the mechanism every time. In fact, it's a lot easier to just jump straight to the product. So let's take a look at this particular example on the worksheet, how you could synthesize this molecule, how to make this molecule using a Malonic ester synthesis. We haven't talked about the second one yet. So this question is asking what would be the steps that you would need to take, and what would be the reagents you would need to use to get this product. Well, anytime you're making a carboxylic acid, you're doing the malonic ester synthesis. The acetoacetic ester, I'll give you a peek at it, not a carboxylic acid produced. So if we're doing the malonic ester synthesis, that means that we are stuck with starting with the actual malonic ester. Like, that's got to be our starting material. And when we look at the product, we need to identify the portions of the product that came from the the malonic ester. So then we will be able to determine which R groups, or how many R groups, need to be attached in this reaction. It's really important that you know that this carbon right here, as well as this carbon right here, they are coming from the malonic ester. When you're making a decision about what to add to the malonic ester, you need to make sure you're getting the correct number of carbons in that. Okay, so our step one is always going to be ethoxide, or NaOET, and then for step two, we're going to add an alkyl halide. And step three, we do ethoxide again. And step four, we're going to do our second alkyl halide. And then step five will be our H3O plus and heat. This is where we do that cool Diels-Alder looking part and turn it into a carboxylic acid. So for steps 2 and 3, this is where we bring in these alkyl groups, and especially on paper, it's not going to matter which order you add them to the molecule. If you're doing this in lab, you just, in terms of bulkiness and steric hindrance, then maybe you're going to want to think a little bit about which order you put them in, but on paper, no big deal. You can also use any halogen that you want, as long as it's a good leaving group, like bromine is always great. And then again, just make sure that you're getting the correct number of carbons in those alkyl halides. So looking at how many, I should really use a different color, how many carbon atoms are you trying to add making sure that you're not getting too many carbon atoms in the alkyl halides.